Imagine this. Every time you use Google Maps to find the fastest route to your favorite coffee shop or track your friend's location, there's a cosmic dance happening overhead, a battle between the fabric of space-time and human technology. Here's the crazy part. GPS satellites in orbit experience time differently than we do on Earth. Their clocks tick faster, thanks to a mind-bending phenomenon called time dilation. Without daily adjustments, your GPS would be useless within hours. That's right. Einstein's theory of relativity isn't just a science textbook concept. It's literally keeping your navigation apps accurate. So how is time being warped? Why do clocks in space run faster? And what would happen if we didn't fix this every single day? Get ready to dive into one of the most mind-blowing aspects of modern science and technology. Time dilation sounds like something out of a sci-fi movie, but it's a very real consequence of Einstein's theory of general relativity. It's the idea that time doesn't flow at the same rate everywhere. And GPS satellites are living proof of this. These satellites orbit Earth at an altitude of about 20,200 kilometers, moving at speeds of nearly 14,000 kilometers per hour. Up there, far from Earth's gravity, time flows just a little bit faster than it does for us down here on the surface. The difference may be tiny, about 38 microseconds a day, but it's enough to throw off GPS calculations by kilometers if left unchecked. So how did we figure this out? What does it mean for our everyday lives? And does this phenomenon have implications beyond GPS? Buckle up, because we're about to unravel the science of time dilation and why it's critical for modern technology. Let's start with the problem. GPS satellites rely on incredibly precise clocks to pinpoint your location. These clocks measure time in billionths of a second, and the tiniest error can cause massive inaccuracies. If the time on a satellite's clock runs even slightly faster than the clocks on Earth, your GPS could think you're in the middle of a lake when you're actually standing on a road. But why does time move faster for satellites? The answer lies in two concepts: gravitational time dilation and relative velocity. Gravitational time dilation happens because gravity affects the flow of time. On Earth, gravity is stronger, which slows time down slightly. Satellites, being far from Earth's surface, experience weaker gravity, so time speeds up for them. At the same time, there's special relativity to consider. Satellites are moving fast, 14,000 kilometers per hour fast. According to Einstein, the faster something moves, the slower its time flows relative to a stationary observer. This effect slightly cancels out the gravitational time dilation, but the net result is still that satellite clocks tick faster. This is where the challenge arises. The discrepancy between satellite time and Earth time may seem minuscule, but it adds up fast. Without constant adjustments, GPS calculations would drift by about 10 kilometers a day. Imagine getting directions to a restaurant and ending up in the wrong city. So how do we deal with this? The solution is as elegant as it is ingenious. GPS satellites are equipped with atomic clocks, some of the most precise timekeeping devices ever made. These clocks are programmed to account for the effects of time dilation. Here's how it works. 1. Initial calibration. Before a satellite is launched, scientists adjust its onboard clock to run slightly slower than clocks on Earth. 1. This compensates for the faster ticking caused by gravitational time dilation. 2. Ongoing corrections. Ground control stations monitor the satellites and send updates to keep their clocks in sync with Earth time. 2. These updates account for both gravitational effects and the satellite's speed. But the story doesn't end there. GPS receivers on Earth, like the one in your phone, play their part too. They calculate your position by comparing signals from multiple satellites. Each signal includes a timestamp, and the receiver uses these timestamps to triangulate your location. Without accounting for time dilation, these calculations would be wildly inaccurate. Let's put this into perspective. Time dilation might seem like an abstract concept, but it's happening around you every moment. Every time you check a GPS-enabled app, you're relying on the precise interplay of relativity and technology. It's a seamless integration of Einstein's equations into everyday life. Here's the most mind-blowing part. If scientists hadn't anticipated time dilation, the entire GPS system would have failed. When the first GPS satellites were launched, skeptics doubted that time dilation would have any noticeable impact. But within weeks, it became clear that the predictions of relativity were spot on. This realization not only validated Einstein's theories, but also highlighted the profound connection between abstract physics and practical engineering. Think about it. Every road trip, every package delivery, every search for a nearby coffee shop is powered by a fundamental truth about the universe. Time is relative. But it doesn't stop at GPS. The principles of time dilation have implications for space travel, satellite communication, and even our understanding of the cosmos. Without relativity, we'd be blind to the true nature of time and space. Time dilation isn't just a quirky phenomenon, it's a cornerstone of modern science and technology. GPS satellites are a perfect example of how theoretical physics shapes our daily lives. From precise navigation to global connectivity, they show us that even the smallest effects of relativity can have enormous consequences. So the next time you use your GPS, remember that you're witnessing a cosmic balancing act, a testament to humanity's ability to harness the laws of the universe for practical use. Time might be relative, but our reliance on it is absolute.